So we just started the recording for this. I will go back over what we skipped. I forgot to do it at the beginning. But what we're doing right now is we're talking about how to configure port B7 for an input. And I'm going to share my screen and we'll look at this. So the way the push button works, it's set up like this. We have a pull-up resistor and a button, and then we have a ground connected here. When the button is open, the pull-up resistor pulls it up to VDD, and you would read a 1. When the button is pushed, the push button, then this is shorted across, which connects it to ground, which causes the point here to be pulled almost entirely to ground because all the voltage gets dropped across this 10K resistor. So when it's pushed, it reads 0. When it's not pushed, it reads 1 or high or true, and false when it's pushed. All right. So to use this RB7, and it happens on the board, on the Viva board, we've hardwired the push button. If you put the jumper on the correct setting, if you leave it on one side, the button's hardwired to be a reset button. But if you change the jumper, now it's hardwired to be connected to RB7 with a pull-up resistor. All right. So now what we do is we want to configure this. So the first thing we want to do is we want to make it an input, and to do that we have to make sure that the bit 7 in the TRIS-B register is a 1, because 1 means input and 0 means output. So we do that here with this instruction. We bank cell TRIS-B and we bit set F TRIS-B, 7. Now by default it should be a 1, but this is still good programming practice, because if somebody took this piece of code and pasted it into another program where somebody had already tried to use RB7 or had already set up the TRIS-B register, cleared all the pins and made them all zeros, made them all outputs, then without doing this, it wouldn't work. Now, it turns out by default, though, it should be correct. So, but we're going to do it just as good programming practice. It also turns out that there are 5 pins of the 18 besides power and ground that do not have analog functions, and for those 5, you don't have to clear the AND cell bit to a 0. But by default, all the AND cell bits are set to 1. But because this pin actually doesn't have an AND cell bit, this is really an extra step. But it's good programming practice, because for all but 5 of those 18 pins, you do have to clear the AND cell bit in order for it to work as an input. And if you don't, it will not work. All right, so bank cell. And we're going to bank cell ANSELB, and then we're going to bit clear F. So here we're setting it, here we're clearing it, making it a 0 for an output or for a digital function. By default, all the AND cell bits that do exist are set to 1s by default for analog functions. Okay, and so we bit clear F AND cell B, 7. So this make digital in. It's also important to do this if you're going to make a digital output, but if you don't do it, it'll still work. It's just bad practice, because it can, depending on what voltage you're outputting, you can cause increased currents on that pin, because if it's still left on the analog thing, it can drive the analog input higher than it should be for certain situations. So they recommend you do it both ways, but it will work. You just probably good practice. You should do it regardless. Okay, now this is all we have to do to configure it. There are a couple of other registers we could worry about. We could worry about interrupts. We could worry about the pull-ups, although we don't really need them for it won't really work for this. We have to use an external resistor because our internal pull-ups are so weak they won't really do the job. And we also can change the level at which we switch from recognizing an input voltage as a 0 to a 1. And we talk about that, TTL versus Schmitt trigger. But for our purposes, VDD and ground are going to work with either a Schmitt trigger or a TTL setting. And it turns out some pins are set to Schmitt trigger by default, some are set to TTL by default. And we normally don't have to mess with them. The only time we really have to worry about that is if is if the voltage of our input doesn't quite get up to VDD or doesn't quite get down to ground, then we have to double check and make sure that it gets low enough to count as a 0 or high enough to count as a 1 based on whether we set it as Schmitt trigger or TTL. So there are a few cases where that might be important, but normally not. All right, so now this is pretty much configured. Now let's write a little routine where we're going to where we want to read that button. So normally we have a couple different ways of waiting on events. One way to wait on events is to wait until an interrupt happens when the event occurs. Now that's a lot more convenient because while we're waiting, we can have a mainline routine that's doing all sorts of other things. Another way to wait on an event occurring is to just have our mainline routine simply keep checking. Check, 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 check in a tight loop. And we call that polling. So when we poll on a pin or poll on an event, then we're doing nothing but checking that event, which if you don't have anything else to do, that's fine. But if you can figure out a way that you might want to do some other things while you're waiting, then you should set it up as an interrupt. And what's really nice about the interrupt, it will automatically interrupt whatever else you're doing when that event occurs if you set it up correctly. And then you can go service that event in your interrupt service routine. And then either in your mainline routine recognize, oh, now we have a flag set up, so now we should go do something else. Or you might do whatever it is you needed to do in the actual interrupt service routine itself. We normally like to keep the interrupt service routine short, though, so we don't usually want those to be too complicated. Okay, so we're gonna illustrate what the software would look like if we're polling on the event, which basically we would do in C with a while loop. In C, we would, let's say we had RB7 all configured. So let me share the screen again, and I'll show you what the C code would look like. So in C, we would do a while loop, while, and in this case, we basically want to wait until we want to do something different when the input goes low. So we're going to wait while RB7, and then and I usually write continue over here. And so what's happened, it will stay on this instruction until RB7 is no longer true. It will be no longer true when it goes low and becomes false. And after that, it drops through the next instruction. So that's in C. In assembly, what we do, we had to configure our input first, and we do in C as well, actually. But now what we do is we create a little loop. We'll call this loop W. And then in loop W, we're going to probably just check this pin. We're probably not going to do anything else. So, or if you wanted, you could blink the LED while you were waiting, maybe one of the colors, just so everybody would know you're waiting on that button to be pushed. You might be doing that too. So you might have something going on in that loop. Okay, so but let's say we're not going to have anything going on. We're just going to test it. So now what we do is we bank cell PORTB, port B, and we actually could put the bank cell before the loop. It doesn't have to be in the loop. And so maybe I'll change this label, put it down here. So we'll bank cell before the loop. And then the first instruction in the loop will bit, let's see, I think it's, let's look at the data sheet, make sure I get the mnemonic exactly right. So in this case, we want to bit test F skip clear. So that's going to be BTF, there's no I in it, BTF skip clear. And it'll be port B, comma, 7. Remember, we have to have that 3-bit extension to tell us which pin we're checking. We have to bank cell it because port B is not in, it's not in every bank, it's only In fact, it's in bank 0. All right. So, and then after this, we're going to have, if it's not clear, then we won't skip, we'll loop. So we'll do a BRA or a go to loop W. So this will take us back to here, unless when we tested bit 7, it was clear, which meant pushed. And if that was the case, it's going to drop through to whatever other instructions we have. We get rid of this. So we do the BRA loop W. We'll go back to here, and then so it'll stay in this tight little loop. Test, test, branch, test, branch, test, branch, and finally, when the button's pushed, test and skip, and drop through. All right, let me stop there. Does anybody have any questions about that? Anybody? Is that good? Everybody tracking?
Yes, sir.
All right. How about the kitty? How about Matthew's cat? Oh, go ahead. Somebody had a question.
Yeah, it was me. Can you hear me?
Yeah.
That was a review for compilers, right? Or for C compilers?
Yeah. So I showed you the C code at the first, right? But then
Yeah.
the rest of the code I showed you was assembler.
Okay, yeah. It was you're going by the review of C PowerPoint, right?
The review of C PowerPoint.
The
No.
C programming.
Oh yeah, I'm using we're talking about assembly language.
Oh, okay. Mm,
Yeah, I just threw the C in as a little bonus.
okay. Thanks.
Yeah, no problem. All right, anybody else? We're all good. Oh, we got 2 cats. Amazing. All right, very good. And we're up to 38. Oh, that's great. Okay, so good. All right, and I will post this video so you can go back and look at it. Okay. All right, so that's the configuring a pin for an input and then polling on a pin. In this case, the push button, but it could be any pin. You could have some external device hooked up to one of the other pins, and you could use exactly the same things, just adjusting for the correct pins and the correct port, and set up the TRIS register and the ANSO registers correctly, and everything would be fine as well. All right, let's look at what we have to do if we load up a couple of variables in 2 different locations, and then we want to write some other code to switch those 2 values. And this is the piece of code that apparently students have the most trouble with, and I'm not sure why. It should be really straightforward, but okay, so let's do that. Let's see. Okay. All right, so okay, so the first thing we will do. So what I want to do now, we're going to load up 2 values in some 2 memory locations. Okay, now the first cautionary thought here, it's often extremely confusing to many students, the difference between the address of a location in random access memory and the data that's held at that location, or the contents of that location. So we have an address and we have data. And of course, the data is just whatever value we put in that location. That location is what we defined as where our variable is assigned. And we usually give that location a name so that we don't have to remember the number. And so that makes it a little bit easier just to, and sometimes if we're really smart, we'll make it the name meaningful. So like we could have it balance in my checking account as the name or something like that. But in this case, because we're not going to use floating point numbers, and because we're only going to do that in C, it's really a little tricky to do that in assembly. So what we're just going to call it, I'm just going to call it X and Y. And I'm going to call 1/3 location V, which will be our scratch register. So the first thing we're going to do is we're going to define where location X is and where location Y is and V, just by writing some code to do that. Now, I actually did that. I did that in the first, I started off, I did that. I kind of got a little confused, I guess, and I already did that. So let's go back and look at where I did that already. Okay, so we have here, we're going to use X, Y, and V, and we're going to assign them to this, to the what's called common RAM. It's the upper 16 locations in bank 0 of the random access memory. And the reason we're doing this is because these are mapped to every bank. So if we use 70, 71, 72, all the way to 7F hex, we don't have to bank cell because they're in every bank. So it doesn't matter what the bank cells, bank register is pointing to, it'll be okay. So that saves us a little bit of code. If we had more than 16 variables we had to mess with, then obviously we're going to have to put some in other places, and we're going to have to use bank cells. But if we can avoid it, it'll save us, it'll run faster and save us a little code writing. All right. But if somebody moves them, then we're going to have to go back and put in bank cells. Okay, so the first thing I'm going to do, I'm going to define X as location 0x70, Y is location 0x71, and V is location 0x72. All right, so I'm going to write that again here. And I use it. I can use a C block to do that. I can use pound define. I'm going to use pound define. And I can't, and remember, I can't use Z because it's a reserved word, which is just the letter Z. And if you use it, you'll get an error, or maybe you won't, but anyway, it won't work. So I'm going to use V instead. And I'll put it in 72. Now, in this case, X, Y, and V are going to represent these numbers, which are locations. But we can put data at those locations, and we can put any 8-bit value we want. We are restricted to 8 bits because it's an 8-bit machine. So we can't deal with numbers a whole lot bigger than 255 without jumping through some hoops. Obviously, C uses 16-bit integers, and so we can go up to 65,000. That's nice. If we want bigger numbers than that, then we have to do some things. And I can't remember if a long is 32 bits or if a long is still 16 bits. It's all compiler dependent. I have to look at that. But if you want to use bigger numbers, you have to make sure that you're setting aside enough room. All right. So in this case, we're just going to put in some 255 or lower than 255, or if we're going to do signed numbers, and again, the assembler doesn't care if they're signed or unsigned because they're not typed. But we as the programmer have to remember how we're using them. And if we're going to consider them to be signed, then we have to take care of all those considerations ourselves. The assembler does not do that for us. But in C, of course, if you declare it to be signed, then C will manage that. And if you declare it to be unsigned, then C will treat it as an unsigned integer. And if you don't specify it, somebody tell me which it is by default in almost every compiler. What do you think? Is it signed or unsigned by default?
Signed.
It is signed by default. And in C, in a microprocessor that we're using, that can be important because it's a 16-bit integer. So if you want to run a for loop past about 32,000 something, then you have to declare it as an unsigned. Otherwise, it'll be declared as assigned, and the maximum unsigned value is 65K, but the maximum signed value is plus or minus 32K, minus 32K plus 32K minus 1. So that can cause real problems if you want to do a for loop 40,000 times. with a sign and you don't declare it as unsigned, it will not work. It'll crap out when it gets past 32,000. It'll suddenly become negative and the compare will fail. So you have to take that into consideration. All right. Okay, and that's in C, of course. But back to assembler. All right, so now we've given an address for X, Y, and V. We haven't given them any values. So this is at compile time. But to give them values, we're going to do it at runtime because I think you can set up. I think you can set up some things where it'll flash the. No, I don't know. I'm not sure you can. I'm not sure you can declare these constants. If you declare these as constants using assembler, it'll put them in program memory and not in RAM, so you can't change them. So anyway, and we want to change them, so we're going to use RAM. And I don't know if you can preset them in RAM. I don't think it'll do that. I think you have to write the code for that. All right, so let's write the code for that. So somewhere in our program, we're going to, we've defined these at the top. Now later down, we're going to, after we start our program, we're going to put some data in there. Remember, the address is 70, 71, 72. The data is coming right now. Okay, so we're going to say, so we will we don't have to bank cell. So what we'll do is we'll MOV literal to W. So let's say we're going to have in 70 we'll put 23, and in 71 we'll put 42. Okay, and we'll just do unsigned numbers. Again, you don't have to declare them because there's no typing in assembly. And then in the V value, we'll just let it be whatever it happens to come up. It will come up a random value. They will not be zeros. All right, so we're going to MOVLW, and in this case, we're going to use 23 decimal base 10. We'll just write 23. And then we're going to MOV W to F X. That's going to write 23 into location 0x70. Don't have to bank cell because it's in every bank. And here you don't have to bank cell because the data is in the instruction, and we're dealing with the W register also in every bank. Okay, and then we're going to MOVLW 42 base 10 again, and we're going to MOVW to F Y. All right, so that configures the value 23 in location 70, which we're going to refer to as X. And but what the X actually means is 70 hex. That's the address. But when we use that address in our instructions, it's going to be looking at that register, which happens to contain now 23. And when we use Y, it's going to be looking at address 71. And that register now is going to contain 42. Okay. Does anybody have questions about that? We're good? All right. Let's go back then. Okay. So there it is. Okay. And so now what we're going to do is we're going to write some code to switch these. Now, it turns out if you really want to get picky, you can do it without using that additional register V that we created in location 0x72. You can use exclusive ORs and actually do it without a third location. But we're not going to mess with that. It's a little squirrely, and I think if one of them's 0, it causes problems. So what we're going to do instead is we're just going to use a scratch register to make it easy. Okay, now since all these registers are in common RAM, we don't have to bank cell any of them. But if they were not in common RAM, we would have to bank cell. And if they were all in the same bank, then we could just bank cell once. But if they were in different banks, we'd have to bank cell every single time we dealt with one of these different ones. But we're not going to do that because that's it's tedious. All right, so the first thing we're going to do, I'm going to save the value of X in my scratch register. So I'm going to do MOV F, move F. Now this one does require that second 1-bit operand. So I'm going to MOV F and I'm going to MOV X into W. But I want it to be in W. I don't want to leave it here and just test it for 0. So I have to put W, X comma W. Now remember, that is 1 bit. It's either 0 or 1. You could also put a 0 there. 0 means W, 1 means whatever the file register referenced by your instruction is, which in this case happens to be X. Location 0x70 in Common RAM. All right, so now we have put the contents of X into W. Now somebody tell me, what does X have?
$23.
That's right. We haven't changed X. All we've done is take a copy of the contents and moved it to W. But 23 is still in X. Okay, now we're going to MOV W to F V. This does not take a second operand. And it puts the 23 we just put in W into V now. V means location 0x72, and now the contents of 0x72 is 23. All right, N is also still 23 in X. But now we're going to move F Y. And we want to put it in W. So we have to put a second operand. The move F instruction requires a second operand. Then we're going to move F. MOV W to F. I didn't do this right. It's MOV W F. Okay. To V. Okay, then we've loaded. Now we put Y, the contents of Y, which was 42. Now 42 is in W, and now we're going to MOV W to F. Doesn't take a second operand, and we're going to put that in X. Now X has 42 in it. We just overwrote the 23. So in doing this, we destroyed the 23 and replaced it with 42. Whatever had been an X is now gone, and now it's 42. And now we're going to MOV F V comma W, and then MOV W F Y. So this is going to take the 23 we saved that used to be an X, but now it's been overwritten with 42, and it's going to put it in Y, thereby effectively switching the contents of X with the contents of Y. And now we're done. All right, so it takes 1, 2, 3, 4 instructions to set these up, and it takes 1, 2, 3, 4, 5, 6 instructions to switch them. Now if we did this in C, we would just say, we would just say X equals 23, Y equals 42. And then we'd say V equals X, X equals Y, and Y equals V. Right? That's how we do in C. But in assembly, we have to take these extra steps. Everything has to move through W. Now, if we had yeah. Okay, any questions about swapping the contents from one register to another? Now, there is a swap command. So let's look at that real briefly. There's a swap command here. But notice, what does it swap? It doesn't swap bytes. It swaps nibbles. Somebody tell me what that means. How many bits is a nibble?
Four.
That's right. A nibble's 4 bits. In fact, way back in the day, some enterprising young engineer, or maybe a group of young enterprising engineers, came up with nibble for 4 bits, byte for 8 bits, munch for 16, and gobble for 32. But gobble and munch have fallen out of use, but byte and nibble haven't. So I don't know if we want to bring munch and gobble back or not. In some ways, it's a lot more illustrative than half word and word. Those are confusing. In fact, even word's pretty ill defined. It doesn't have to be 32 bits. It can certainly be different. But generally, we talk about a word as 32 bits. All right. Okay, let's configure a register now. Okay, so an example of a register could be the TRIS register. So let's look at the TRIS register. We'll look at that in the data sheet. So I'm going to go pull up the index again. Let's see, it's this. No, this. So let's go to the IO ports. And then if we look, again, we've got port A, B, and C, and each one of those ports has several registers. All right. So we'll talk about, well, 2 registers to keep in mind is the APF-CON0 register and the APF-CON1. These registers can change which pins certain functions are assigned to. And one of the things we're going to do is we're going to use the UART on RC5 for receive, and we're going to use the transmit on RC4. But by default, if you look at it, and for 14-pin devices, which would be the 1825, not the one we have the 1829, that's a 20-pin device. By default, it's set to 0, which means it's set for RB7 to be the UART transmit line, and up here for the 20-pin devices, it's set for the by default RB5. So RB5 and RB7 are the default UART lines, but we are going to switch them because we're hardwired to C5 and C4, and we use an RB7 as a push button input, so we don't want to use that. And we're using RB5. We're using RB4 and 6 as ICE2C, and we're using RB5 as an analog input. So we have to switch these. So somewhere in our code, we're going to have to address the APF-CON0 register when we start using the UART. But for right now, we don't have to worry about it. And there's also an APF-CON1, and it flips around some of the bits. When we do PWM, by default, the CCP2 output is connected to RC3, and we want to use it on the green LED, so we can change the brightness of the green LED using PWM. So we have to change this bit in UART in APF-CON1. So just file that away. We're not going to use that for a while. But other than APF-CON0 and CON1, the only registers we talk about with respect to the ports are each port has these registers. Each port has a port A register, and this is the register we use to read the port. Each port has a TRIS register, which sets the direction of the pin, whether it's an output or an input. Each port has a latch register, which we use to write an output to the port. Each port has an AND cell, which we use to set and clear bits. Now you can see here, believe it or not, let's see, this is A. So port A has an AND cell bit for bit 0, 1, 2, and 4. Does not have one for 5, and doesn't have one for 3. 3 is our master clear pin. 5 is connected to our green LED. But bits 4, 2, and 1, and 0 do have AND cell bits. Now bits 0 and 1 are being used by our Snap programmer debugger. So we just can forget about these bits entirely. We're just writing them off and using them for our programmer debugger. We could use them, but then we wouldn't be able to debug our code and use them at the same time unless we bought a special header that would allow us to do that. And that's what, when you have that, when you create a new project and you after you pick your chip and then it says, are you going to use a header? You say no. And that's where we would say yes, and we'd specify which header, and then we could use all these bits and also use our programmer debugger at the same time. But we're not going to use that special header. Okay, so down here we have another register that all of them have, and this is called the weak pull-ups. These are so weak, they're useless. The only real value for them is we generally like to turn them on if we're not going to connect anything to the pins. So if you're going to do a nice finished routine, you should go in, and any pin that's not actually assigned to a specific function that's just going to be unconnected, you want to go ahead and turn its pull-up on. Just reduces noise coming in on the pin, basically. And you don't want it to be an output, you want it to be an input, so it won't accidentally get shorted out or something. So anyway, so we typically only use those for that one purpose, and that's it. And then finally, we have the input level register, where we do choose between whether or not it has Schmidt trigger levels used to differentiate between a 0 and a 1, or whether it uses TTL levels. Now, anything that's really close to 0 and really close to VDD will always read correctly. But there's a point in between those two levels where it switches, where it clearly becomes a 1 or clearly becomes a 0. And those are slightly different for Schmidt trigger and TTL. And by default, you can see pin, so this is port A. So by default, pin 0, 1, 2 is by default set up to be Schmidt trigger. And then the rest of them are by default set up to be TTL. Sort of interesting. So they're not even set to the same defaults. And most of the time, this makes no difference whatsoever. But if you have some peripheral device that's not sending an output, like say maybe you're running your chip at 5 volts and you have a connected device that's running at 3 volts and it's sending its input in, and then the question is, will 3.3 volts for a high, will the chip recognize that as a 1? And in most cases, it probably will. I have to look. It's possible, though, that might be one case where you might want to have to check Schmidt trigger versus TTL and make sure you've selected it correctly, because you might get, it might be more robust if you pick the right thing. All right. So anyway, so that's what every port has, these 6 registers: the input level, INVL, INLVL A, weak pull-up A, Ancel A, latch A, Tris A, and port A. And we have the same for B, C, and if we had other ports, they'd have the same stuff. And there is a little diagram here that shows how these pins work. I'm going to talk extensively about this later on. Let's see. It's kind of up here. Not there. Here. I'm going to talk about this diagram, but just give you a quick overview. Here is your pin, typical IO pin. Could be port A, port B, port C pin. Here, when you want to read it, you have to read the port X. When you want to write it, you should write the lat X. You can also write the port X, but don't do it. There's a little potential rare problem that can occur with that. So it's better just to use the lat where you won't have that problem. And that has to do with the read, modify, write way almost all micros deal with their ports. And so if you want to read the latch, then this is what you're doing. You're gating through this buffer the output of the flip-flop onto the data bus. If you want to read the pin, you're reading the port, and it's gating the pin through the data bus, assuming this AND gate has the correct AND cell bit selected to be a 0, so it will actually read the pin. Because if it's a 1, it's going to go off in here to some analog function instead. And then if you have this set as an output, the Tris bit will be 0, which means it'll turn this buffer on and it'll connect the Q of this flip-flop. And there is a flip-flop associated with every pin except for A3, because A3 is master clear and it doesn't have an output function. but every other pin has a flip-flop, and this tris bit, if it's cleared, will gate the output of that flip-flop onto the pin. Now, these two diodes here are protection from static. Okay, we'll come back and talk about this more in class, but it's important to look at this diagram to understand how these pins are managed. And this is very similar. Almost all pins are just like this in other micros as well. All right. So we talked about the APF Con 1 and Con 0 registers for switching which pins are connected to our UART and which pins are connected to let's see, what is it? It's connected to our CCP. Okay. So, all right. So now we've looked at that. All right. So now we want to go back to here. And all right. So let's say we want to configure. Oh, okay. Well, let's say we want to configure one of those registers. So the tris register. So let me just temporarily go back to that. Okay, so we'll look at let's look at tris C. We'll go down here to tris C. Okay, there's the tris C register. Now I'm just going to copy that. So we have all 7 pins in tris C are implemented. Now what do you notice? All tris registers default to 1s on reset and power up, both. So they will be set as inputs by default. And if you want to use it as an output, you have to change that. Okay, so let's do that. And oh, and by the way, on the outputs, what are the latches on power up? It's let's see. Yeah, it's power up and should be power up, readable. Yeah, power on reset and brownout reset. Okay, on power on reset, the value for all these ports is going to be unknown, which means they can be anything. So your pins could output, if they're set for outputs, they could output 1 or 0 because these will power up in some unknown state. And then on brownout, though, they're going to read a 0. That's interesting. I didn't know that. All right. Well, anyway, okay. So let's go back. Didn't want to do that. Let me do this. Okay. We will drop this down. All right. So let's okay. So let's configure that register, which we've already done, but I just want to show it a little differently. So here's my tris register. So I usually like to draw it out. So I'll usually draw a little box here. Now, this works great for registers that are all 8 bits. When you get to 32-bit registers, forget it. I'm not going to do this. It's too much drawing. So this is pin 0, and this is pin 7. And we'll say this is tris A. All right. Okay, so now, tris C. So let's say we want to have C0, C1, and C5 as output, and we want to have C2, C3, C4, C6, and C7 as input. Then, so how would we configure this register? Well, so for as an output, we have to have a 0. So C0, that's 0. 1 would be a 0. 2 would be a 1. 3 would be a 1. 4 would be a 1. 5 would be a 0 here. 6 and 7 would be 1s. So now, what do we write into the register? Well, we configure it all of once by doing 1, 2, 3, 4. 1, 2, 3, 4. So 2 hex digits. This would be D. 1101 equals D, and 1100 equals C. So our value that we'd want to write would be 0xDC. All right. So to configure this register for this particular arrangement, we would simply do bank cell TRISC, and then we would do MOV literal to W 0xDC and MOVWF TRISC. Okay. And that would make C0, 1, and 5 outputs, 2, 3, 4, 6, and 7 inputs. Now we could also do that with bit set and bit clears, but it would be a lot of bit sets and bit clears. We could also do it with a mask. And there are other ways we could do it. But in this particular case, that's one way we could do it. You can also call this value 0xDC. You could just call that your mask if you wanted, and you just write that straight to the register. All right. All right. It's not really a mask, though. It's just a value to write to the register. Okay, I think with that, I've covered most of what I wanted to cover. Let me take 1 second. I'm just going to go back through and mention the very first thing that we did, since I didn't put this on. So if we were doing a assembly language for loop, we have to have an index. So in C, we would just write for x equals 0, x less than some limit, x plus plus, and then we would have the curly brace and a bunch of stuff and a curly brace. That's the way we do it in for. In assembly, we have to have an index as well. So I'm going to use, in this case, I'm going to use this V location as my index, and I'm going to preload. We want to do this loop, say 15 times. So I'm going to preload 15 into V by doing an MOVLW and MOVWF to V. And then I'm going to bank cell latch A. I'm going to bit set it. So that's going to turn it off. I'm going to call delay. Then I'm going to bank cell latch A and turn it on. And then I'm call delay again. And then I'm going to use this instruction that makes these for loops really easy to do. Decrement F, skip on 0, V, comma F. Now remember, this does take that second 1-bit operand, which tells me I must leave the result in V, not in W. And that way, when I take V, I started at 15. The first time through, I decrement 1. Now it's 14. It isn't 0. So then this go to instruction is executed, and it goes back up here to loop Z and does this all over again. And then the next time it's 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Oh, you can't see that. Sorry. So it counts 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. And if you count those up, that's 15 times. On the 15th time, when this instruction is executed, and remember, you have to have the F here, then it will, the value of V will finally be 0, and it will skip the next instruction. Well, the next instruction is this go to instruction, or branch always, to go back up here. So it's going to skip that and continue with the rest of your code. Okay, so that's how the assembly language for loop works. Okay, with that, I think I'm gonna give you a chance to ask questions, and we'll wrap it up. Does anybody have any questions about that? So remember, go ahead.
No, I had a question when we were doing simulating a while loop in assembly. You used the command branch, BRA.
Doesn't matter. The only difference between branch. So if we look at the data sheet, okay, let's look at that real quick. Frankly, the only reason that instruction is there is for backward compatibility to legacy code. That's really it. But let's look at that real quick. So if you look at the down here, chapter 29 instruction set summary, and you go down and look at all the instructions. Well, actually, you can look at this. Here's the branch always instruction here, and here is the call or go to. The go to has an opcode from bits 13, 12, and 11, so a 3-bit opcode, and it has a 11-bit literal, 11-bit. Down here, the branch always has an opcode 13, 12, 11, 10, 9, a 5-bit opcode, and it has a 9-bit literal. So it's a difference between a 10-bit address and a 9-bit address. and remember, your branch instructions are 2's complement based. So you either go, so you take half of the 9 bits. So that's 8 bits. So you can go forward 256 instructions or backwards, or forward 255 instructions and backwards 256 instructions. Whereas with the branch always, you can go forward. Let's see, did I do that right? No, this is 11 bits. So it's 10 bits. So I can go forward 1,023 instructions and backwards 1,024. Whereas with the branch always, I can go forward. I can go forward 255 and backwards 256. That's the only difference. Now, the only reason they didn't use this for some other function was because in the old days, they didn't have a go-to, they had a branch always, I guess. I don't know. But anyway, because they had that BRA instruction a long time ago, they just left it in. But obviously, it executes at exactly the same speed, takes up 14 bits like all instructions. So there's no real advantage to using a BRA versus a go-to. The only advantage is if you have to go further than 255 instructions forward or 256 back, you have to use the go-to. If you have to go more than 1,024 back, back, or more than 1,023 forward, now you either have to place an intermediate branch instruction at that location to get you on down, or you have to use the assembly language. You have to preload the PC latch high and the PC, and then you write the PCL with the lower 8 bits of a 15-bit address. And you can do that. It's not that difficult. You could use the label, and you can take the upper bits of the label and the lower bits of the label, or you can shift it and get that done. That's all set up at compiler time. So when you run the code, it'll have the right values to put in there. But that's kind of extreme, really pretty rare you'd have to do that, but it's not impossible because you do have 8K of program code, and you can only go essentially plus or minus a K. So if you had a 3K program and you wanted to go from somewhere close to the beginning to somewhere close to the end, you can't do it with your go-to or your BRA. So there are limits to those that you have to kind of keep in mind. All right, any questions about that? Was that what you were asking? I guess I jumped ahead there a little bit.
Yeah, it makes sense now, the difference between the two.
Legacy. Okay, anybody else? All right, are you guys staying warm today?
I had a question about lab 1.
Go ahead, Matthew.
When do you want us to turn it in?
Okay, so here's the deal. What counts and allows you to get a grade in the course is to demonstrate your laboratories to the TA in the lab. The little quiz or the turn-in sheet plus the quiz, I'd like you to do those and turn them in. I use those. They don't count for a whole lot, but if you're, say, right on the threshold, I might look at that. So they maybe count less than all of them together count maybe 1 course point. Okay, so it could help you if you're right between 2 grades. It might boof you up, or it might prevent you from getting boofed up. So I want you to turn them in. But what really counts to get credit for the lab, you must demo it. Turning in those sheets does not give you credit for the lab, nor does it prevent you from getting credit if you don't turn them in.
Okay, got it.
And that's from doing lab